Right, here we're going to use mathematical induction to prove that 1 plus 2 plus 3 plus n is equal to n times n plus 1 over 2 for all positive integer values of n. Okay, so we start off with our required to prove, and we are required to prove that 1 plus 2 plus 3 plus n is equal to n times n plus 1 over 2 for all positive integer values of n, and that would then mean that n is greater than or equal to 1. Now, in terms of our proof process that we follow, the first thing we need to do is verify that our statement is true for our base case. Now, our base case we get from this over here, where we know here that for n greater than or equal to 1, so that means we're going to be verifying for n equals 1. That's our base case. So our first step is verify statement for n equals 1. And what we need to do is show that our left-hand side equals our right-hand side. So on our left-hand side, well, if n is equal to 1, what we've got there is just a 1. So maybe we just put an equal sign there, so that's equal to 1. If I have a look at my right-hand side, well, that means I'm going to be putting in, I've got n plus 1 over 2, and that's just going to be 1 times 1 plus 1 over 2. 2 and 2 divided by 2 is 1, and that's equal to my left-hand side. So therefore I can say my statement is true for n equals 1. Now, we call this beginning part our initial statement. Okay, the next part of our proof is our inductive hypothesis. And that sounds very fancy, but what we're going to do is make an assumption that our statement will be true for n equals k. So our next step is assume that the statement is true for n equals k. So all that means is that I'm going to put a k in to every value of n. So what I'm looking for then is that n can take on values of 1, 2, 3, etc., all the way up to k is a positive integer. Okay, so in other words, what I'm going to say is that 1 plus 2 plus 3 plus k is now going to be k times k plus 1 over 2. So notice all I've done is I've replaced my n's with a k. Now, that feels like I'm not making any progress here, but this is a crucial step in our inductive reasoning. So this we call our inductive hypothesis. Okay, now the third part of a proof by induction involves that we have to prove that the statement is true for n equals k plus 1. So now I'm required to prove that my statement is true for n equals k plus 1. Now the k plus 1th term is the term after k. Okay, so in other words, what I'm saying is 1 plus 2 plus 3 plus plus k plus 1, my next term, is equal to, now instead of k, I'm going to have k plus 1 times k plus 1 plus 1 over 2. So I can simplify that a little bit. So I've got 1 plus 2 plus 3 plus k plus 1 is going to be k plus 1 times k plus 2 over 2. And that's what I need to show. All right. So I'm going to say, well, on my left-hand side, so the left-hand side is this whole thing over here. And what you might see or recognize is that I have got part of the left-hand side which is made up of my inductive hypothesis, where n is equal to k. And that is important because I can actually substitute my right-hand side from my inductive hypothesis into that left-hand side. And I'll show you why that's important. Okay, so on my left-hand side, I have 1 plus 2 plus 3 plus k plus 1. That's my left-hand side. And this whole thing over here, I actually know is k times k plus 1 over 2. And then I'm adding my k plus 1. And I need to tell my teacher that I know why I'm doing that. So I'm going to say, using the inductive hypothesis. Okay. And now what I need to do is simplify and work with this to make it look like this right-hand side. So I've got two separate fractions here. Let's combine them with the lowest common denominator. So k plus 1 over 2 plus 2k plus 1 over 2. And that then gives me k squared plus k plus 2. And that gives me k squared plus 3k plus 2 over 2. And I probably need to shrink this a little bit so that I can fit the last little bit on. Let's just do that. Okay, and I can factorize k squared plus 3k plus 2. That can become k plus 1, k plus 2 over 2. And oh wow, look, it looks exactly the same as my right-hand side. So I can say that equals my right-hand side. So therefore, my statement is true for n equals k plus 1. And then I need to make my final mathematical induction statement. So this is the fourth step in the process. My statement is true for n equals 1, 2, 3, etc. k and k plus 1. Therefore, by mathematical induction, my statement is true for all positive integers greater than or equal to 1.